There we go. All right. All right, so this chapter is all about aldehydes and ketones, and so where we left off last time was discussing these reactions of aldehydes and ketones that we covered before, or rather these reactions that produce aldehydes and ketones, these oxidation reactions, right? So if we take a primary alcohol and we oxidize it with a weak oxidizer, we get an aldehyde. If we take a secondary alcohol and we oxidize it, regardless of whether we use a strong or a weak oxidizer, we get a ketone, okay? So given what we discussed before, let's just kind of remind ourselves, looking at actual reagents here. So let's say that I take a primary alcohol. What's going to be the difference between if I use DMP versus this sodium dichromate in sulfuric acid and water? Everybody take a second and see if you can give me the product of these reactions. Yeah.
Do we have one more example in the final?
Yes. Yep. All right, and then we can actually do the same thing, but now we'll move this hydroxyl group to create a secondary alcohol. Boom, boom. All right, so which one of these is our weak oxidizer? The DMP, right? So this one we classified as weak. The other one we classified as strong. And let me just say that this chromium right here should be the indication that we're talking about a strong oxidizer. We've kind of defaulted to this sodium dichromate. There are a few other ones out there. So for example, CrO3, chromium 6 oxide, also a strong oxidizer. I don't know what it is. Chromium's just the magical transition metal that is really good at oxidizing carbons. So anytime you see chromium, you think strong oxidation, okay? There are a few reagents that we could use, but they all have that same transition metal, chromium Cr. So our weak oxidizer will turn a primary alcohol into an aldehyde. Does our weak oxidizer react with the secondary alcohol?
The weak one?
Yep. So it does. And what do we get? Not an aldehyde, but what do we call it when it's in the middle of a molecule? Name of the chapter. Aldehydes and ketones. So we get a ketone. Okay? With our strong oxidizer, if we have a primary alcohol, we get a carboxylic acid. All right, and what do we get with our strong oxidizer and a secondary alcohol? Do we get a carboxylic acid? No, we just get that ketone again, right? We can't further oxidize this thing here. It gets stuck, right? So that's what this chart here is telling us. Primary alcohols, we can oxidize them once to aldehydes, or we can fully oxidize them to a carboxylic acid. But a secondary alcohol kind of gets stuck at this step here. You can't further oxidize it. And a tertiary alcohol, you can't oxidize at all. Okay? All right, so given that, let's just think, what's going to happen if we take our aldehyde and we use that strong oxidizer, sodium dichromate, and sulfuric acid. Can we oxidize this aldehyde? Okay? In the same way that our strong oxidizer will take a primary alcohol all the way to a carboxylic acid, right? It blows right past that aldehyde step, fully oxidizes it. Yes, we could oxidize an alcohol to a carboxylic acid. So if we take our aldehyde and use that strong oxidizer, we will get a carboxylic acid. All right, the strong oxidizer will fully oxidize anything that it comes into contact with. Aldehydes can be further oxidized, so a strong oxidizer will oxidize to a carboxylic acid. What about if we take our ketone? Can that be further oxidized? No. So, if we take our ketone and we hit it with this sodium dichromate, doesn't matter, it can't be further oxidized. We're stuck at that step there. Okay, so just like we can oxidize primary alcohols all the way to carboxylic acids with strong oxidizers, we can oxidize aldehydes, but not ketones, to carboxylic acids. So we can just say explicitly, aldehydes can be oxidized strong oxidizers to carboxylic acids. All right, so these oxidation reactions we talked about as ways to convert alcohols to aldehydes or ketones. Let me grab a subset of these slides here. All right, so we talked about how going from an alcohol to an aldehyde or ketone we called oxidation reactions. We can actually go the other way as well. All right, so these are some new reactions that we're going to learn about for this chapter. These are what are called reduction reactions. Okay, so in oxidation, we're creating more carbon-oxygen bonds. In reduction, we're creating fewer carbon-oxygen bonds. We're breaking carbon-oxygen bonds. All right, so again, I'll spell it out rather than using our little symbol. Going this direction is an oxidation reaction. Going the other direction is what we call a reduction reaction. We've talked about oxidation before. Oxidation reactions create new carbon-oxygen bonds. Reduction reactions are the opposite. They break carbon-oxygen bonds. All right, and so we talked about these oxidation agents. Okay, now we're going to talk about these reduction agents here. And there's going to be two of them that we learn about. Truthfully, if you go on in your organic chemistry knowledge, you'll sort of learn the difference between these two. But for our purposes, they're going to do the same thing. They're both going to reduce both aldehydes and ketones. Okay? They are both what are called hydrides. Which are compounds with nucleophilic hydrogens, which is just kind of bizarre because remember, nucleophiles, these are these things that have negative charges. Hydrogen is not something that we associate with having a lot of electrons, okay? So these compounds are kind of weird. They have these hydrogens on them that have a butt ton of electrons. So there's going to be two of them that we learn about. The first one is called sodium borohydride. And what that's going to look like is NaBH4. This is really the important bit here, our reduction agent. If we're going to draw sort of the full sort of arrow here in terms of solvents and all that, these reactions take place in ethanol. All right, and there's a second step where you add acid. All right, but the hydride, the actual thing that's doing the reduction is that, specifically actually the BH4 part. All right, and the other one is lithium aluminum hydride. And that is LiAlH4. So again, that H4 is really the important bit. These reactions take place in diethyl ether. And again, you have a second step where you add some acid. So these are our two reducing agents here. Okay? And again, both will reduce aldehydes and ketones. All right, so bottom line is for our purposes, just file them both in the same place in your brain. They're both doing the same thing for us. They're reducing these aldehydes or ketones. to alcohols. All right, so let's just look at a specific example real quick. What if I have the following ketone here? What's going to happen when I treat it with sodium borohydride? Everybody take a second and see if you can't predict what our product would be. All right, so we can count carbons. We're going to have the same number of carbons on both sides. This is not a bond that or a reaction that creates any new carbon-carbon bonds. All right, but I'm going to reduce this ketone functional group. I'm going to get rid of a carbon-oxygen bond, leaving me with just a secondary alcohol. All right, so these are the exact opposite of the oxidation reactions that we learned about. We're just going the other direction now. All right, so I'm going to put a few more down.
It wouldn't change to a chlorine group with the HCl?
No, it does not. The HCl actually just puts, it's not really involved other than this hydrogen here is that hydrogen there. We don't really look at mechanisms. Really, we just want to be able to identify this thing here as a reducing agent, turning that carbonyl into an alcohol. Oh, sorry. Let's use our other one. All right, actually, that is a very good question because HCl does react with alcohol groups. I'm being a little lazy though. This is really dilute hydrochloric acid, really any acid, but a very dilute concentration. So not enough to react with our alcohol group. All right, so we're going to turn our ketone into just a carbon-oxygen single bond. All right, same number of carbons, still got that six-membered ring. Same cyclohexa, yeah, go from cyclohexanone to cyclohexanol. All right, and then here is kind of a big ugly branched molecule, but I'm just going to draw my same carbon backbone structure here. 1, 2, 3. But again, I'm going to turn that carbonyl group into an alcohol. So we can even sort of make a note here. We're doing the same thing every time. Reduction, we're breaking a carbon-oxygen bond. So we're turning, whoops, that's not how you spell that. A carbonyl bond into an alcohol. All right, the opposite of our oxidation reaction. So sorry, just to go back to our products here. Okay, so first sort of new set of reactions that we're going to learn about with aldehydes and ketones. Aren't too bad because it's the opposite of these oxidation reactions that we learned about before. These are these reduction reactions going the other direction. All right, and the other big reaction of aldehydes and ketones. So I say that. I'm going to save one type of reaction for aldehydes and ketones for next week. They're kind of a pain in the butt, so I want to dedicate a few lectures to it rather than rushing through this week. Okay? For this week, we're going to button up all the other reactions. And so really the other one that we're going to cover and spend a lot of time on, we've also already done before. Grignards, right? These are also reactions of aldehydes and ketones. These are going to be an important part. I know they're very tough, so it's good that we're circling back to them here. All right, but we got to remember these Grignard reactions, how to get our products, and we'll work on going backwards as well. Given the products, how do we figure out what reactants to use? So let's just remind ourselves what these Grignards are. Right, so I'm going to take my aldehyde or ketone, and I'm going to react it with my Grignard reagent here, which contains that magnesium bromide portion. So this is my actual Grignard reagent. Grignard reactions create new carbon-carbon bonds. All right, they also turn carbonyl groups into what functional group? What is our functional group in our product of a Grignard reaction? What is it? Somebody said it. Alcohols, okay? So, not unlike the reduction reactions that we just talked about, this carbonyl group is going to be turned into an alcohol group. But importantly, we're also going to create a new carbon-carbon bond. And that's what makes these reactions kind of a huge pain in the butt, is that we get this big, ugly product because we're linking these two molecules together, right? So when we're finding our product here, the first step is to identify which two carbons we're going to have our new bond between, right? So identify carbon in our ketone or aldehyde that has the new bond. And so which carbon is that in this case it's a ketone, where I'm going to draw my new carbon-carbon bond? Yeah, what do we call that carbon? It's got a special name because the type of bond it's in. Carbonyl carbon, right? So this one right here. So we got to identify our carbon in our aldehyde and ketone that will have the new bond. That is our carbonyl carbon. And then we're going to identify the carbon in our Grignard that will have the new bond. All right, and which one is that? The one at the base of the magnesium. That one doesn't have a special name, unfortunately, but yes, the one at the base of the magnesium. Carbon bound to Mg. All right, so then we're going to draw our new carbon backbone. Linking those two carbons together. So pay special attention to your carbon in your, how many carbons you have in your ketone and how many carbons you have in your Grignard. You're going to join these two molecules together, creating a new bond between these two here. So everybody take a second and draw your new carbons here. All right, so I'm going to draw my 1, 2, 3, 4 carbons from my ketone. And I'm going to mark that one that we said should have the new bond. I'm going to draw in that new bond. All right, so on the other side of that has to be that purple carbon from my Grignard. And then I have to include, this would be 1. So I have to include 2, 3 carbons on there, right? So 2 more. All right, so there's all my carbons. We got one thing missing. We said that we're going to turn this carbonyl group into an alcohol. So the last thing that we're going to do in our little list of instructions here is to add that alcohol group to what used to be your carbonyl carbon, to formerly all right, so I was pretty good about keeping track color-wise here. This green carbon is what used to be my carbonyl carbon, so that's where my alcohol group is going to go. All right, so kind of good news, bad news thing here. Grignard's kind of a pain in the butt. They're going to be a big part, right? They were featured in the ethers chapter as well as the aldehydes and ketones chapter, so we can definitely expect to have a few of those problems on our exam. Good news is we're covering it again, so we got one more lecture to practice this sort of stuff. All right, but yes, these are reactions that we definitely want to know very well how to predict the products for. Okay, so let's just do a few more product predictions here. right, so again, going to identify the carbon in this case it's an aldehyde that will have my new bond. That's my carbonyl carbon. And the carbon in my Grignard with the new bond, that's the one at the base of the magnesium. So now I'm going to draw my carbons in my product, connecting these together. So I'm going to start 1, 2, 3 carbons over here. That makes this one my green carbon. So if I'm going to draw my new bond, on the other side will be that purple carbon. All right, so now I just got to include all the other carbons around that purple carbon. All right, so we got one over here, one over here. Boom, boom. And then one of those has these 2 extra on there. We'll make it this top one. All right, and then I'm done?
No.
What am I missing? That OH functional group, right? And which carbon is it going to go on? The one that used to be that carbonyl carbon. All right, and remember you can rotate about these single bonds, and what I mean by that is if you drew your structure with these 2 sort of branch points coming off of this carbon, that would be the same, right? Just kind of rotated about that one bond. Either one of those is equivalent.
Is the same situation for the alcohol? The orientation doesn't matter?
As long as it's attached to that carbon right there, yep. All right. So same game here. Let me make a little bit more room for myself. Now we have, and you'll notice that when you start with a ketone, things are a little bit more crowded in your product. It can be a little bit harder to draw. You just got more carbons going around that bond. All right, so here, that's my carbon with my new bond in my ketone. Here's my carbon with my new bond in my Grignard. So again, let's start by drawing these, in this case, this ring. All right, and this carbon here has that new bond. So on the other side of that bond has to be that purple carbon, right? Because that's my new bond there. So then I'm just going to include that other one. So that would be that carbon plus one more. Boom. And then again, need to remember to put that alcohol group on that green carbon, that formerly carbonyl carbon. All right. So then last one here, this is going to be a big ugly product. But if we follow our steps, we'll get our correct answer, get it linked up together or correctly. So this is my carbonyl carbon. That will be one carbon with a new bond attached to that carbon there. 1, 2, 3, 4, 5. So here's going to have my new carbon-carbon bond. Okay, so on the other side of that is the purple carbon. And then I just got to include everything attached to that purple carbon, these 1, 2, 3, 4, all in a ring here. And then again, last step is to put that alcohol group, that hydroxyl group, on what used to be that carbonyl carbon. All right. Rings in particular can be kind of easy to add or forget a carbon or something like that. So what's that double check that we can always do? Just counting carbons, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. Always go back and double check by counting your carbons. Especially if it looks a little weird when you're done with it, right? Just kind of like an easy double check to do. All right, so then one more, and we're going to just practice all these reactions next class, but just to kind of finish it off here. I want you to tell me, we'll do a simple one here. Give me one aldehyde or ketone and a Grignard that you could use to create the following alcohol. All right, so there's actually two ways that you could have done this, okay? Because looking at this product here, there's really only one thing that we know for certain, and that is that this carbon here has to be the carbonyl carbon. All right? But either this or this could be our new bond. So let me just show you the two ways that we could do this. Again, all we really know is that that has to be our carbonyl carbon. So if I'm going to say that this is my new bond here, that means that these are going to be my aldehyde. All right, I'll keep it colored here. And the other carbon, it's just this one methyl group here, has to be my Grignard. Okay? Or I can say, all right, this must be my carbonyl bond here, or rather my carbonyl carbon. And this is my new bond. So that means that this chunk here is my aldehyde. And the other portion, I guess I didn't color that, is my Grignard. Okay? And we kind of talked about how Grignard reactions are like kind of super powerful. It really doesn't matter what your Grignard is. There are some reactions where we had this logic behind which sort of combination would be better. For Grignards, it does not matter. Either one of these would be just as efficient at producing that particular alcohol. So absent any other information about how many carbons your Grignard should have or something like that, either one of these answers would be perfectly acceptable. These are two perfectly acceptable ways of creating that alcohol using a Grignard reaction. All right, so we'll just practice this a whole bunch more next time, and then we'll learn our